Hey everyone, oh my gosh, it's Wacky Wednesday. I gotta re-hit the button. It's Wacky Wednesday. Wacky Wednesday. Grabbing a quick snack. I think that's gonna reset Crash Bandicoot. Good to see you here, Noel. Good to see you here, Braden. How's everyone doing? We are going to get started with some chapter 10, I believe. Chapter 10. I'm gonna send out a big announcement. So we've got class coming up. Good, it's almost Friday. I know, it's almost Friday. Gotta get down on Friday. Is that the name of the lyrics? Mewbot is here. See, look, he's already saying good in the chat. So Mewbot is back again, I think, today. I don't know why. Sometimes the computer says yes, Mewbot. Sometimes the computer says no, Mewbot. You never know if Mewbot's going to be here, apparently, in recent times. It's a 50-50 shot with Mewbot. Why am I getting a duo push? I thought I was already logged in. But I guess I'm not. Should we do some chapter 10? Chapter 10, does that sound like a plan? Or no chapter 10? Chapter 10 or no chapter 10? What are we going to do? What shall we do? Computers is trying to take it. They are. I was using AI just a little while ago. I got everything. ChatGPT. Okay, we need to tell everybody that today is a big, big day. Because what are we going to do during class? During class, we are dropping how many points? 66 minutes till class. So let's, big bonus today, be there live for 10,000 points. At some random point during class, we will drop 10,000 points if we break 300. Let's go! 300. Click here. Okay. Okay, we got it. There we go. We got the link. Double check the link. Link is good. And we got it. And we're going to send it out. Okay, let's hit 300. Let's make it happen. How about some chapter 10? Chapter 10 is a tough one. And we've already done the homework. So what should we do? Braden, Noel, thank you so much for being here. With Mewbot here, I can hit the point button. I can hit the points. You just got 1,000 points right there. You got 1,000 points. My monster shirt is going a little bit crazy. Let me see right here. I'm going to go just check this camera. I knew I shouldn't wear this shirt today. Camera green screen. 1 second. Trying to find the camera. Chapter 10 on canvas content. Oh man, Braden, you're so good. Camera green screen. Is the filter on this? Where's my filter? That's me, right? That's not me. There's two me's? There's two me's. What? How can that be? Why are there two Brians? That's weird. Okay. It's two me's, apparently. Let's remove one of those me's. Brian times 2 right there. Just having a little fun as we get started. Let's remove that Brian. Bye-bye, Brian. Okay, that didn't destroy anything. Where am I? Who am I? What am I? There I am. Okay, that's me. I found me. So I found me, but I can't find any of my filters on me. There's color correction. Woo! Is that better? I don't know. It's the green screen filter correction, and it's supposedly camera green screened. And here it is right here. Clay, good morning. I was just doing some chroma keying. I don't know if it's better or worse. It's always trying to make a good chroma key right here. You're not supposed to wear yellow. Like, yellow is actually kind of close to green. You're not supposed to do it. What are we working on? I finished Camp Fun for a random question that was confusing. Got my answer correct, but using the bus stop sample you did yesterday, but I was wondering if you could go over it. Yeah, which one do you want to go over? Let's pull up the Canvas content right here. Let's do some actual work. It's office hours, so let's do work. Brian's just having some fun trying to correct things. Mubot is here, Clay, which means we got points. More points in the chat. Which one was it, Noel? Do you remember what the question was like? So we're going to pull up the Canvas content and let's go check it out. What is the question on the Canvas content? Remember what it was like? Canvas content. What is the question like on the Canvas content? The probability of a new marketing campaign being successful? Yes, and that one is just like you said it perfectly. So let's go do that one over here. Okay, so we're going to do the probability of a new marketing campaign being successful. Let me get loaded up with some worksheets right here. And we have a lot of our work from yesterday, which is really good. You'll see it here in a second. And here we are. So we got it all up. Let's go grab the sheet. Okay. And let's go preview it. We want to do the new marketing campaign ones. We're probably going to go through till we get it. Here it is. We got it. So this one's a little bit easier because you can guess, but you have to know how to do the math. So these are the steps, and let me put this in the notes, for solving an at least one problem. So this is called an at least one problem, and students get stuck on this on the test. So we'll put this in the notes right here, solving an at least one problem. Never rub your eyes. You won't be able to see. Stat 201, chapter 10 or chapter 12, at least one problems. Okay. So when I'm solving this right here, you'll notice I'm not going to go straight to the answer. I'm going to do the steps you would do to solve this if you have no idea what you're trying to find. So it says right here, a new marketing campaign has a 30% probability of success. So what should I write to start? Does anyone know what I'd write with this information right here? The new marketing campaign has a probability of success of 30%. So I'm highlighting some key things that should clue you in on what I want to write. So I want to summarize this, and I want to write this out in a way that makes it easy to understand. So new marketing campaign has a probability, correct. So how would I summarize that? Look what I've highlighted. So what would I write to summarize this? How would I summarize this? What would I put? What would I write? Remember what we wrote yesterday? So look at what we've highlighted. Probability of success of 30%. So what would we do? If you're watching this video now, try to write ahead and you'll be practicing the steps. I'll give some hints. The first thing I would write is probability. Kind of, yes, we'll go in that direction. You got it. Well, if we know the probability of success is 30%, I think Noel's on the right track. What do we know? What else do we know? Noel's looking at the complement because either something's a success or it's a failure. And you could say not a success. That'd be the complement. So we have right here, and Clay's on the right track too, 30% probability success. And now we have probability of failure is equal to 70%, not a success, exactly. Now here's the thing. We have just written the what. We have just written the what, which is everything that can occur. Notice we're reviewing concepts. This is every single thing that can occur, known as the what. My eye. Contact goes full circle in my eye. This is known as the what. What's it called? Well, the R probabilities. This is the sample space, which is everything that can occur. The sample space is all possibilities. So when you think about a sample space, you're like, well, this could happen, sample something, right? There's the sample frame, which is everyone we can choose from, all people we have access to, or things we have access to. Then there's the sample space, which is all possible outcomes when it comes to things occurring. So this is the sample space of outcomes. The sample space of outcomes, either the project will be a success or a failure. Now, when you think about this, it actually gets pretty complicated pretty quickly. Let's say I wonder if ChatGPT could generate this. I'm going to images right now and sample space of 5 coin flips. Man, it'd be nice if they showed that. I'm going to try that on ChatGPT really quickly over here to see if it does it. I'm going to say create a picture of the sample space. Create a picture of the sample space of 5 coin flips for heads. So we're going to see if it creates the picture. Oh my God, it might even be, it's generating a picture. This is, if it does it, if it does this right here, this is going to be absolutely insane. I don't know what's going to generate, so let me not. Okay, so we're having ChatGPT generate a picture of a sample space of 5 coin flips. Oh, it's kinda. Coffee image, kinda. No, it's wrong. Interesting. So we're not there with AI yet. It generated this picture here. Picture can't be taken. I'll show you the picture. It is interesting. It definitely did not know what I wanted, which is kind of neat. So here's the picture it generated. That is not right. Let me say this. Write out the sample space of possibilities in a table for heads and tails for 5 coin flips. Last try right here. At this point, I could have almost written it out. It takes a while to write this out. There we go. Yes, here we go. It is doing it properly now. This is the sample space of 5 coin flips. Does it make sense what a sample space is? People in the chat, do you understand what a sample space is? Like when you flip a coin 5 times, you could get heads, 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 tails, heads, 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 tails, heads, 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 tails, tails. These are all the possible outcomes of everything that could occur, and you're finally going to get to tails, 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 all tails at the end. So these are the possible outcomes. Now I could say this. Rewrite this same sample space of 5 outcomes where we have success has a probability of 30% and failure has a probability of 70%. Add a column on the far right that shows the probability of this outcome. Now, we're reviewing some key terms right here with this. Exactly, the sample space is all possible outcomes. Like in one coin flip, it's heads and tails. And in multiple coin flips, it would be the sample space of like, if you have 2 coin flips, it's easy to write. Like, what's the sample space of 2 coin flips? Can anyone, these are test questions. Can anyone tell me the sample space of 2 coin flips? What's the sample space of 2 coin flips? So you have to think all possible outcomes when you flip a coin twice. See in the chat right now if you can write the sample space of 2 coin flips. In the chat, can you write the sample space of 2 coin flips? And good work, Clay. Let's throw you some points. Mubot's back. So what's the sample space? So you have to think, Brian wants to know all possible outcomes. This helps you review the terms. Sample space of 2 coin flips. What would it be? What would the sample space of 2 coin flips be? See if you can get... Well, it's not 25. Those are actually the associated probabilities. You are correct, Braden. You are correct. Let me throw you points. That is correct. The associated probabilities for each one of them, like heads, heads, is 0.5 times 0.5. So you are correct. So that would be the probability of one of the observations. They're not always even because things aren't always 50-50 probabilities. But what would the sample space be? What is all possible outcomes when you flip a coin twice? So a sample space is all possible outcomes. What are all possible outcomes when you flip a coin twice? Heads, 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 tails, 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 heads, tails, heads. Great job, Noel. Yes, that's the sample space. That's everything that could occur, just like we did. And then we actually do the combinations right there, Clay. We do heads, tails, tails, heads. If you look at this sample space, it takes into account which order things occur in. And then here, I'm going to get the... right here, I'm going to get the full sample space for the success or failure of a campaign. And you'll see right here, all the combinations. It's calling it flip still. Success, success, success. And there's the probability of all successes. Here's the probability of the last one being a failure. If you notice, with the F, it really doesn't matter. It doesn't where the F is at, it's going to be one failure right there. They all don't have 1/8 probability right here because there's 32 combinations. But sometimes, if you notice, failure is more likely. So the most likely thing would be that they're all failures. So the most likely outcome will be 0.7 to the 5th power, which is all failures. Does it make sense how this is computing right here? If you watch what this is doing, if you notice there's 2 failures, so you have 0.2 or 0.7 to the 2nd power, and there was 3 successes. There were 4 failures here, so you have 0.7 to the 4th power, and you times it by the 1 success. So a success and a failure and a failure and a failure and a failure. That's how they're getting this number right here. And you get down to the very end, we only have one. We got one more to go, I think. No, we're getting close. There's a lot of things that could occur. And if you had to write all this out, this would take quite a lot of time to do. And I think we're finally near the end of it. Yes, I think it's going to do it now. Failure, failure, failure. 0.7 to the 5th power. So how in the world would you figure this out when it comes to this question? Would you write out this full sample space? No. To solve an at least one problem, we do it in an easier way. It says, what is the probability of at least one success? Well, tell me this. It's going to be either the case, and this is the key to solving at least one problems. There will either be all failures, as in every campaign will be a failure, or what? It's the case that every campaign will be a failure, or what? So this is every campaign was a failure. It'll be the case that every campaign was a failure, or what? What is the other side of this? Be very careful, not the other side, but like, what is everything else that could occur? It's either the case that everything will be a failure, or what? There will what? It's either the case that there will be all failures, not all good. So all successes is just this over here. Not everything will be a success. There'll be at least one success. And if you take a look, and a lot of people say that. That's why I pause on this. Does it make sense that either everything will be a failure, or there'll be at least one success? Because everything above this is one success, at least one success. So it's not that everything will be everything will be all successes, or everything will be all failures. Everything will either be all failures or at least one success. At least one success. Does everyone follow that? That's the key. Because what you have to write right here is either they will all be failures or at least one success. And since this is everything that can occur, the probability is equal to what? Since this is everything that can occur, the probability of this right here written out is what? So it's either all failures or at least one success is 1. And you can see it visually over here because we encompass the whole table. Notice how this probability right here, they would all add up to 1 if we just add up everything above it. So wait a minute. How can we get the probability of everything not this? Because we know the probability they're all failures is 0.7 to the 5th power. How could we get the probabilities of at least one success? How could we get the probability of at least one success? How could we figure out the probability of at least one success? Because we just did the probability of all failures, like the first is a failure, and the second is a failure, and the third is a failure, and that would be this right here, the probability of all failures. How can we figure out at least one success? Which is what we want to find. We want to find this. We can algebra, right? How do we algebra? So we want to figure out this. Just go right here and do the following. Just go like this, and algebra, do 1 minus, or minus this from the other side, and you algebra it over there, and you have the answer. And remember, it was like 17% or so. It was like 17 point something, 17.8, I believe. We can double check over here. 16.8, excuse me. So this is 16.8. And here we'll do one more line on it. And yeah, then it is equal to 0. There we go. And if you need to know how to do these, but you can always ask, like, for that last example, what is the probability of at least one success? Should put a question mark on that. Should be 0.832. It's going long. Look, we could have figured that out. So what I would do if I was a student right now, see now it literally is doing the same thing we did. It's doing the complement. It's saying the probability, it's doing it that way. It's doing it the quick way. So good idea on it right there, doing the complement of 1 minus the probability of no successes. So all failures, yeah. Probability of at least one success is equal to 1 minus the probability of no successes. So it already went and solved the equation basically and then found the answer right there. How about this? Yep, great job, Noel. Come up with 5 at least 1 problems for me to try and solve. Don't tell me the answers, but get them when I ask for them. Okay. So how many of these can we do and how quickly can we do them? So this is at least 1 extreme practice. A lot of people can't do this on the test. They say, I have no idea how to do these problems. So here we go. Here's our problems. Let's bring them over here. Who can do the first one? Does the light bulb one? Okay. At least 1 6 on 3 dice rolls. What's the answer? At least 1 6 on 3 dice rolls. So you get it. Someone says, I'll give you $1 million if you roll a 6. And you have to roll a 6. What's the probability you'll roll a 6? Does anyone know? I'm trying to do it in my head because I can almost do this one in my head. Numbers are just gains 216. I can't be right. I did it wrong. Oh, it's 216. It is 216. Really? Probability of at least 1 6. Wait. Yeah. Oh, well, let's look. It's going to be 75. Try to do it in my head. 91 over 216. So that's about 40-ish%. I think it's this. Yeah, okay. That was in my head though. So what am I doing? When you do problems like this, you have to write it out. So what's the probability of at least 1 6? So how are we going to solve this? We're rolling dice. If someone says get at least 1 6, what would be bad for us? If someone says, yeah, we'll do the one next here. Yep. So, and that's at least one problem. If someone says, we'll throw that one into the mix here, Clay. If someone says you have to get at least 1 6, what would be very bad for us? We want at least 1 6. So what would be very bad for us? Like we're not going to win the money. What would be bad? At least 1 6. What do you mean by nothing? I think you're on the right track. We'll either get at least 1 6 or no 6s. So when you think about the probability of a 6 on a dice, dices are fair. The probability of getting a 6 is 1 6. So we go over here and we write probability, all 5s, or it's so the probability of a 6 is equal to 1 6. The probability of not 6 on a dice is equal to 5 6. Does that make sense? Those are you either get a 6 or you don't get a 6. So what is the probability of getting no 6s? What is the probability of your first dice is not a 6 and your second dice is not a 6 and your third dice is not a 6? So you get not 6 and not 6 and not 6. What is the probability of not getting a 6 3 times in a row? What is the probability of you don't get a 6, you don't get a 6, you don't get a 6? Do these steps every time you're doing it till you get really good at it. So you have to practice these steps. Like, what is the probability of not a 6, not a 6, not a 6? What is the probability of not getting 6 3 times in a row? What is that probability? You don't get a 6. Correct. And put in, that is correct. I think you would have done it correctly, Noel. Just make sure the 1 6 is inside of a parentheses right there like that. That is correct. Great. Oh, wait. That's not the probability of not a 6, not a 6, not a 6. That's the probability of all 6s. So you are right to raise it to the third power, but that would be you get a 6, you get a 6, you get a 6. That's the probability of all 6s. This is the probability of not all 6s, because the first one has a probability of 5 out of 6 of not being a 6, and the second one has a probability of 5 out of 6 of not being a 6, and the third one has a probability of 5 out of 6 of not being a 6. So now we just algebra. So we take this over here and we algebra. And here was my guess, 42.2. And then we go 5, 6, 2, 3. There we go. There we go. I was trying to do 5 cubed in my head and 6 cubed in my head and dividing 125 by 216. And I guesstimated 125 by 216. Or then I minused it and got, yeah. So I was doing that in my head, I was like, too much math, trying to solve about 40%. So does that make sense? We're going to do Clay's question next right here. For the next 4 stops was probability. And so this one right here, good question, Clay. We'll do bus stop canvas problem. I'm going to put this in the notes. You ready? We're going to do Clay's problem and let's do the practice. You ready? So when you're doing these problems, let's review the steps. Okay. So here's the problem. The first thing we do is because of the 3 dice rolls, right, Braden? You got it. So you raise to whatever times, like how many times it occurs. Like you roll the dice 3 times and you don't get 6 3 times, raise to the 3rd power. And we'll see that same. You're going to see lots of practice. Like I want you to be pros at this by the end of class and during or by the end of office hours. So this is the boot camp for it. Okay, so we have a bus arrives on time 55% of the time. So as you practice this, the first thing you should write out is your what. So if they roll the dice 6. Yep, exactly, Braden. Yeah, what's the probability of getting at least 1 6 and 6 dice rolls? 1 minus 5 6 to the 6. Yeah, that would be it. Like everything but not all 6s. Great job, Braden. The first thing, if you're practicing writing these out, is to write out your what. I also did for that last question. The first thing to write out is to write out your what. The first thing to write out is to write out your what. I'll write it out if you tell me what it is. Like, it's everything that could occur. First thing to write out is your what. This is the practice to make sure you're doing things right. You have to like go step by step, take notes, and be very meticulous. So the first thing is to write out your what. What do we write out first? What's it called? There's a hint up here. The sample space. The possibilities, which is true. The sample space is the list of all possible outcomes. So you have the probability of on time. And the probability is on time is this. And we have the probability of late. This is not a multiplication. It's a statement of probability of late. You do not do P times L. It's just literally a sentence. The probability the bus is late. And the other one is probability the bus is on time. So now we have the probability the bus is late, the probability the bus is on time, and they are complements, meaning they add up to 1. So the bus will either be late or on time. When you think about 4 stops right here, there's a lot that could occur. 4 stops could be late, 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 on time, late, late, on time, late, late, on time, late, late, lull, and late, late, on, late, on, late, on, late, late, on, late, on, late, late, on, late, on, late, 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 on, late, on, late, on, late, on, late, and on. There we go. This is the sample space. This is, no worries, Clay. This is the sample space. Sounds like the buses are here. This is the sample space. What is the probability the bus is on time for at least one of the stops? Which one should I highlight in pink for I don't like it? As in, we are not going to be interested in that one. Which one of these should I highlight? Because it says, what is the probability it's on time for at least one stop? Which one of these are we not talking about? So what would I say right here? Which one would I highlight and be like, that's not the one we're talking about? Which one would be the one that I would highlight and say, like, that's not the one we're talking about? It says on time for at least one stop. So on time for at least one stop. Well, so it's either going to be on time for at least one stop or always what? It's either going to be on time for at least one stop or what? It's either going to be on time for at least one stop or always what? It's either going to be on time for at least one stop or always what? It's either going to be on time for at least one stop or always what? Or always late. This is what we want to find. Notice how it's on time at least once. Does that make sense? In all of these occurrences, it's on time at least once. The one that we're not interested in is the one where it's always late. So can't we just do the following? Well, we could actually write it a bit quicker this time and say everything but always late equals on time at least once. Does that make sense the way we've drawn this out? Like, I think drawing it out can help, especially when you're practicing, that everything but. If you want to go to the starter way of doing it, you would write to begin, the sample space of what can occur is the bus will always be late or on time at least once. And then you can algebra the other one over. Does that make sense what we're doing right here? Like, this is where you have to know, like, okay, so we got to write this sentence where we say either the bus is always late or it's on time at least once, because these occurrences of always late and on time at least once is everything that can occur, and the sample space, which is what this is equal to 1. The sample space has a probability of 1. Sample space has a probability of 1 is rule number 2 of probabilities. How are we doing on the logic and the theory behind what we're doing right now? It really comes down to knowing the building blocks of, like, why are we doing this? And hopefully the pictures help out. So now we just have to figure out the probability it's always late. What's the probability it's always late? On 4 stops, what's the probability it's late, and then it's late, and then it's late, and then it's late? What's the probability of it being late 4 times in a row? What's the probability of late, and late, and late, and late? Notice I'm saying and. When we say and, we're multiplying. It assumes that the buses are independent, which is maybe true for this. But what's probability it's late, and then it's late, and then it's late? Probability that it's late, and then it's late, and then it's late, and then it's late. Ran out of room. What is the probability that it's late, and then it's late? Not quite. No, it's not 50-50, though, because the bus isn't late 50% of the time. Close, Clay, very close. That would be true if it was 50-50, but this bus is a 45% probability of being late, and thus we would do this right here, because the bus has a 45% probability of being late. So you would go right here and say the probability, so it'd be 1 minus the probability of late times late times late, and we just substitute in the probability right there. So that's, great job, Noel. And that's going to be the probability on time at least once. And we have to subtract them. We have to go here and go 0.45, 2, 3, 4. There we go. There it is. Probability, and that's what would go in on time at least once. So does that make sense, Clay? And great job, Noel, right there. We plug that into, it comes out to about 4%. 1 minus 4% is about 96%, and there's the exact numbers. Can we get another one right here? Let's see if we can do this one. At least one tail on 5 coin flips. This one's easier. This one's easier. Let me see here. 2, 4, 8, 16. No, something's wrong. Oh, it should be 32. Well, then that's not hard. That's too easy. At least one tails. So 31 over 32, an 8, 12.5, 6.25, 6.125, 3.067, 3.067. I'm trying to see it. So 96.925, nice, 96.925. Last little bit I couldn't hold in my head. So what you would do for this one is you would say either they are all, so at least it's probably at least one tail. So either they're all heads or at least one tails. I'm gonna ask you to do the next one here. Let me go back to doing more practice. So Noel and Clay and Braden, get ready for the next one. I want to see if you can solve it. So this one right here, you would solve out the probability of all heads. And the probability, this one is, Clay, like what you just did. The probability of all heads is 0.5 to the 0.5 to the fifth power. I think I just turned on the effect. No, I muted myself. Good. 0.5 to the fifth power. And then you would take that and subtract this over to the other side. And I think I did it correctly. And so here we go. That would be 0.5, 2, 3, 4, 5. There we go. Oh, I just did the math wrong at the end. Well, when I was trying to do it in my head. So there is the probability of at least one tails. This one's interesting. Ooh, I like it. Nice job, Clay. Good work. How about this one? So let me mark this, though, in the notes. Say we're doing more at least one problems. 39, 23. Stat 201. Chapter 12. More at least one. At least one defective product in a batch of 10. A factory produces light bulbs and 12% are defective. If you randomly test 10 light bulbs, what's the probability at least one is defective? So give it a moment right here. Who's got it? Can we hear music again? I think we can. Who's got this? Yeah, we can hear music again. What do you think? If you get good at solving these, they're very quick. You just have to keep practicing, and then when you get stuck, be like, oh, what did I do wrong? Write your sample space to begin. Hoping people watch this in the future, especially with the test coming up. Week and a half till the test. So a factory produces light bulbs and 2% are defective. If you randomly test 10, what is the probability of finding at least one defective bulb? At least one defective. What do you think? Nice job. That is right, Braden. Braden, 1,000 points. You did it. We can actually use the binomial applet for this, where you type in 10 samples with a probability of defect of this, and it is most likely that you have 0 defective, and it might be actually very hard to see, but this is the probability none are defective. Yeah, you're finally getting it down, yeah. And so I think it should be about 18.3%, and we'll write the sentences Braden wrote. 2, 3, 4, 5, 6, 7, 8, 9, 10. There it is right there. So that has got it. So probably what Braden wrote, and if you start to get this down, Braden probably wrote, it'll be the case that either all are good or at least one defective. This was a tough one, Braden. Great job. So it's either the case that all the light bulbs are good, like every one of them works, or at least one is defective. Does this sentence make sense right here? So shout outs to Braden. We'll throw some extra points on that. So remember, if you're here talking, you get the points. So it's either the case that all the light bulbs are good or at least one is defective. So Braden then went in here and said, well, what's the probability they're all good? The probability they're all good is the probability of one being good 10 times in a row. And then Braden just algebraed this over. And once you algebraed it over, you get the following equation. So we just take this, we bring it over here, and we do 1 minus, and there it is. That's what Braden got. Really good work, Braden. Great job. I'll give you a Owen Wilson wow.
Wow.
Yeah. At least one person with the same birthday of 23 people. Oh, man. This one's actually really interesting. Which actually, they're kind of going to... Nice job. Braden's showing some knowledge. I like it. And so with this right here, this goes to the birthday problem on Wikipedia. And if you get enough people in the same room, around 23, you actually see people have the same birthday. See if you can solve this one. And you'll notice what happens as you get more people in a room. Did they pick the number? They picked 23. So we can actually see the answer on the screen right now. It's going to be 51% or so. So with more people in the room, the probability of at least one person have the same birthday as someone else increases very high. If you have 50 people in the same room, the odds of people having the same birthday are like 97%. If you have 90 people in the room, it's virtually impossible no one has the same, at least 2 people have the same birthday. Would you like 90 people, at least 2 people have the same birthday? Yeah, it's the way math works. So how does the math work? Well, what's the answer to this? How are we getting 51% right here? Can I get my quiz? Yeah, swing by. I do quiz checks in person, so come by office hours today. We'll get it worked on. So, and we did corrections, right? Swing by in-person office hours. We can work on stuff and fix up stuff. Advertisement right here. And so what would this one be? Maybe Braden will get it. Maybe Clay will get it. Maybe Noel will get it. What do you think? What do you think? What will this one be? I'm debating getting a Monster Energy drink. I need to kick the habit. How bad is Monster Energy for you? How bad is it? I'm addicted. I'll solve it in one moment right here. Get the energy drink. It's like a treat. I only had 1 cup of coffee this morning. Got like 7-8 hours of sleep, so that's good. So, with this problem right here, it's either the case that no one shares a birthday from the pod. Go to the you can go to pod if you want. Oh, because you might have like $90 or something. I always just go into the Student Union with Vicky and everyone there. I think Aiden and Vicky are there. I can't remember everyone's names, but check out Student Union with Vicky. She's awesome. Everyone loves Vicky. No one shares a birthday, or at least one group shares a birthday. Does this make sense? So we want to figure out at least 2 people share a birthday. So we need to figure out the probability of no one sharing a birthday. We're talking to 23 people. What's the probability no one shares a birthday? Oh, they're doing it the hard way. Okay, so this one is actually more complicated. Maybe I'll show you. So this one is non-independent probabilities. This wouldn't be too tough for the test. The probability that the first person does not share a birthday with the 2 people do not share a birthday would be 364 times 365 for the first person. Then you would multiply by, the next person has to have one of the remaining, that'd be right? No, I think this is right. Let me double check. Yeah, you just lower that number. You don't lower both numbers because one of the days has been taken and you have to keep multiplying because every time someone enters the room, then the probability of them not sharing a birthday changes. So this is not independent. And that's a good review of what independent means, is that one probability would not influence the other. So you would then keep lowering this. Does that make sense theoretically? Who follows? This one got a little more complicated. They chose one where it's not independent probabilities, because once you have 30 people in the room, your event, or 23 people in the room, you're going to get to a probability. Well, the first person being unique is that, because the first person will not share a birthday with anyone else because no one else is in the room. The next person can pick from 364 of the 365 days and be unique. The next person can pick from 363 and 365 and still be unique. And then you go all the way down here and you've subtracted 23 from this, so you'd get all the way down to 42. So I could say solve what I'm trying to solve for me and write the full equation in it. ChatGPT is nuts. I could say, show me the answer to each question and the math. You flip a bias coin. What's the probability is heads and tails is 60-40. What's the probability of getting at least one heads? It'd be not all tails. So it'd be 1 minus 0.6 to the 4th power. So why stop at 42? Which one for why stop at 42, Noel? Which thing for why stop at 42? Was it the one I was just talking about? Oh, so this is because 23 people are entering into a room. So you go, the first person walks in, the second person walks in, the third person, I think I've done it properly. Actually, I think it is actually here, because that's the first person, the second person, the third person, the fourth person, the fifth person, and you keep on going down. What is inferential statistics? The ability to make inferences into populations. The ability to infer things about populations. That's why we call it inferential statistics. We infer things. And so now we can actually see all the different maths we were working on. The 42% we got. Here's the one. Is this the one Braden got? So, here's the one Braden got with the light bulbs. Great job, Braden, on the light bulbs. Here's the birthday problem. And if you notice right here, this is what it did. And it goes down to 343. So that's the birthday problem right there. There's the 343. And there's the mathematics. It's about 49, 50%. Using the complement rule, oh, there it is, because they found that. And then it would be, this is the probability no one shares a birthday. 1 minus it is the probability at least one person shares a birthday. And then this was 1 minus 0.6 to the 4th power. And there it is right there. The all tails is this. So 1 minus 0.6 to the 4th power. So is, oh, but that would be everybody is unique. That would be 365 people enter a room and everybody's unique. So show the math for 365 people entering a room and everyone having a unique birthday. Show the full equation. So this is the full equation. You'd have the first person enters the room and the second person enters the room and the third person enters the room. I don't know if it's actually going to show all the... It's not going to... Oh gosh, we need to stop this. See, it's showing like... Or is it doing the full equation? Oh, see, it did the ... It's cheating. But does that make sense, Noel? This would be if all 365 birthdays are unique. This one goes a little bit beyond the class, though, because these are not independent probabilities. Because the first person walking into the room, they will be unique because no one's in the room to share a birthday with them. The next person would have to have one of the remaining 364 days. And then you notice I'm saying and. Here's what you need to know for your class. If I say and, you need to what probabilities? If I say the word and, you need to what probabilities? So if I say and, you need to what probabilities? Multiply. Yeah, this one. And so here's multiply. Definitely check out the review sheet. We'll bring up review 2 here. So let me do one last thing to end that's super class related. And let me put in the video as big advice for the test. And then we get energy drink as a reward. Okay, make sure to save this. Mubot has the link right here for exam 2 review. Don't worry about getting this wrong, but I want you to tell me when you'll click a button right here. Start a poll. Here we go. Okay. Okay. When we add 2 events, they need to be what? I was a little bit mean. If we're adding 2 events, you might be on the right track, Clay. Don't worry about getting this wrong. I wish I had done the one that's on the screen. I didn't do the one that's on the screen. I did the synonymous version of it. The reason I'm pointing this out, and if you're watching this in the future and you're seeing this is test 2 advice, is we have questions on the test that talk about when we multiply events, they need to be independent. Independent and dependent are just opposite sides of the coin. But we have right here, when we add 2 events, we use the word or, and they need to be mutually exclusive. What is another word for mutually exclusive? Another way to say mutually exclusive is to say that 2 things are what of each other. So what is another word for mutually exclusive? Mutually exclusive is synonymous. I want you to see what mutually exclusive looks like. That's what mutually exclusive looks like. Mutually exclusive. This is what mutually inclusive looks like. Not complement. Good guess. Good guess. Mutually inclusive. Now, complements are mutually exclusive, but they're not synonymous. The synonymous term is disjoint. They share no commonality. This is jointed. So notice they have an overlap when A and B occurs. The definition of mutually exclusive or disjoint is that if A occurs, B cannot occur. If something is jointed or mutually inclusive, if A occurs, B can occur. It's not that B must occur, it's just that it can occur. So if you think of, I say only one person gets this puppy, and there's a bunch of people standing around. Well, only one person is getting the puppy of these 3 people. And so if you get the puppy, everyone else doesn't get the puppy. So that would exclude them from getting a puppy. If we think about Brian drinking coffee and Chelsea drinking coffee, is that a mutually exclusive event or not a mutually exclusive event? So Brian, yes or no? Yes, it is mutually exclusive if Brian drinks coffee, Chelsea drinks coffee, or no, it is not mutually exclusive. Brian drinks coffee, Chelsea drinks coffee. Is that mutually exclusive or not mutually exclusive? What do you think? So you have to say, here's how to check it. Brian drinks coffee, can Chelsea still drink coffee? Is there any point in the world when Brian drinks coffee and Chelsea drinks coffee where both A and B occur? Or is it the case that every time Brian drinks coffee, Chelsea cannot be drinking coffee? So what do you think? They're mutually exclusive or they're not mutually exclusive? What do you think? Exactly. So since we can both drink coffee, they're what? Mutually exclusive or not mutually exclusive? They are mutually exclusive or they're not mutually exclusive? What do you think? Since we can both do it, they're what? They're not mutually exclusive. So here's how to check it. Brian can drink coffee. Chelsea can drink coffee. It happens at the same time, which means you're down here in the not mutually exclusive. They are including each other, as in it can occur at the same time. How about this? You get your grades in a class, so they're jointed exactly, which means we can't add them together easily. When you get your grade for Stat 201, are grades mutually exclusive? Your grade for Stat 201, only for Stat 201, as in, can you make an A in Stat 201 this semester and this semester also make a C? Your parents say, how'd you do in Stat 201? You said, well, I made an A this semester for the whole grade and I made a C for my whole grade. You're correct. You can't do that. There's one grade. So all of these grades are mutually exclusive of each other. They're not complements, though, because making an F is not the complement of making an A. You can, however, describe them as complements if you say something like, the complement of making an A is not making an A, and that is mutually exclusive. So complements are mutually exclusive because you can't make an A and not make an A. But complements are not just what mutually exclusive means. Complement is either this or not this, but that is by definition mutually exclusive. Does that make sense? So you have to have a good definition of mutually exclusive. Mutually exclusive is when one thing happens, the other thing cannot happen, which actually is what complements do, but that's not what a complement is. Complements are mutually exclusive, but a complement is either A or not A. Brian drinks coffee or he does not drink coffee this morning is a compliment. Brian gets his energy drink or he does not get an energy drink is a compliment. So right there, that's got it. And my big advice on test 2 is know the formula sheet. It literally tells you things like A and B can be added together if they're mutually exclusive. A and B can be multiplied together if they're independent. So with that, we're going to head out. Bye for now, everyone. Bye.